continuing with sequences, and we're going to start off with a theorem called the sandwich or the squeeze theorem. So, suppose we have sequences an, bn, and cn such that an is less than or equal to bn, is less than or equal to cn for all natural numbers n, and then further suppose an and cn both converge to alpha, some real number. This implies bn converges to the same alpha. That is not what I want to draw. Okay, so you can see why it's called the sandwich or squeeze theorem. So it's essentially saying if we've got two sequences and three sequences, and one of those sequences is sandwiched between or squeezed between two other sequences that converge to the same limit, then that sequence in the middle therefore must have the same limit. So with this suppose, we're saying if this condition and this condition is true, then this implies 3, okay? So 1, if we have 1 and 2, and plus 3, okay? So let's just dissect this a little bit more. An, bn, and cn in the brackets represent the sequences. An, bn, and cn without the brackets are the terms in the sequence. So every term in an has to be less than or equal to the corresponding term in bn, which has to be less than or equal to the corresponding term in cn. So a1 has to be less than or equal to b1, has to be less than or equal to c1, a2 less than or equal to b2, less than or equal to c2, so on, all the way up to an less than or equal to bn, cn, and goes on forever. Okay. So let's look at an example of how we can use this relatively simple theorem, and the trick really is, so we'll probably be given some sequence, bn or whatever it's called, and we want to manipulate this in some way so that we can find two sequences that we know satisfy these properties, and that will give us, and that we also know the limit of, and that will give us the limit of our sequence that we're looking for. So we're going to have a sequence xn that's defined by the individual terms xn being equal to 1 over n sine of 4 over n cubed. We want to use the sandwich theorem to find the limit of this as n tends to infinity. So this is a sequence, so remember n's in the natural numbers are kind of important. We know that sine for all real numbers as inputs here, and therefore sine of 4 over n cubed, because 4 over n cubed is going to be a real number. It's bounded between minus 1 and 1, so minus 1 less than or equal to sine 4 over n cubed is less than or equal to 1 for n in natural numbers. Since n is a natural number, 1 over n is greater than 0, so we can multiply through by 1 over n. Let's just say, well, we can do this since 1 over n is greater than 0. So now notice that this is our xn. This is what we've been trying to get in the middle of this sandwich or squeeze, and minus 1 over n tends to 0 as n tends to infinity, and 1 over n tends to 0 as n tends to infinity. So this is property 1, this is property 2, that's not property 1, sorry. Property 1 is this one here. So we have 1 and 2, and you don't need to write it like this. I'm just, as I'm going through an example, trying to show every step. The rest of the work would suffice without the 1s and 2s. Therefore, 1 over n sine 4 over n cubed tends to 0 by the sandwich theorem. As I say, you could call it the squeeze theorem. So that's all we're going to look at in this video. If you did find it useful, please be sure to like the video. I'd encourage you to try your own examples of this. We pick quite a simple example. It's quite nice when we have sine and cosines involved, because of the fact we know they're bounded by minus 1 and 1, this creates this double inequality that we can then manipulate. Yeah, the more you do it, the more you'll get an intuition for which problems can actually be solved with the sandwich theorem. This can also be used not just for sequences but for functions too. Yeah, it still holds. But in that case, it has to be, the inequality has to be true for whatever domain you're working with. Here we're working with the natural numbers. So yeah, more videos to come on sequences and series further down the line. Please check out the previous videos in the series if you haven't already. I'll link the playlist. But for now, that's it, and I hope to see you in the next one.